I'm going to talk today about smart contracts. My presumption is that not everyone here is familiar with smart contracts, so I'm going to begin with a short tutorial and high-level overview. A smart contract, in essence, is a program that runs on a blockchain. I'm not going to have time, of course, to talk about blockchains, but suffice it to say that given trust in the blockchain that underpins a smart contract achieves a few essential properties. The first is that it's transparent, in the sense that all of its state and behavior is visible to the entire world. Second, it's irreversible, which is to say that once it's performed an action, no adversary, and even the creator of the program itself, assuming the program was suitably instrumented, can undo the actions of the smart contract. And third, and perhaps most importantly, it's tamper-resistant. By that, I mean, again, an adversary, even the creator of the contract, can't subvert its control flow, can't change the behavior of the contract. Smart contracts also have this very interesting property that they can act on money in the form of cryptocurrency. They can do so directly, which is something that ordinary software typically can't. There's been a huge amount of interest in smart contracts, and in particular in Ethereum, which is the largest public smart contract platform today. To give you some sense of the scope here, as of this morning, Ethereum was worth more than $92 billion. Well, we have a lot of academics in the audience, so as a useful point of comparison, suppose we were to take the 3 richest universities in the world and add up their endowments. You would get less than the value of Ethereum. And heck, you could even throw in a sort of garden variety Ivy League school like the one I work at, and you still have less than the value of Ethereum. To be fair, the market capitalization of Ethereum exceeds that of all but the largest, perhaps the 8 to 10 largest banks in the US as well. So it's a really substantial phenomenon. Why this tremendous interest in smart contracts and Ethereum? Well, suppose that 2 players, Alice and Bob, want to trade. Bob has created a new cryptocurrency called Bob's Bubble tokens. And I'll explain in a moment what tokens are. And Alice wants to buy some. So Bob is going to sell 10 of these tokens to Alice for 1 ether, an ether being the unit of currency in the Ethereum platform. Well, they have a little problem here. Bob might be polite and say, Alice, please, you go first. Send me your ether. But then, of course, there's no guarantee that Alice is going to get the tokens in return. And vice versa. Bob sends the tokens, he has no guarantee he's going to get the cryptocurrency. This is the classic problem of fair exchange, and it's a very challenging one. What they really want, Alice and Bob, is to be able to appeal to some trusted third party, somebody everyone in the world trusts to behave in an even-handed and open and honest manner. What they really need is Oprah. Right? This would make life easy, right? Because then Alice could send her ETH to Oprah, Bob could send his asset, and Oprah could then redistribute their assets in a fair way, atomically. So in this case, Oprah is acting as a trusted third party with public state. Everything she does is visible to the whole world. Unfortunately, Oprah is generally booked. So what are Alice and Bob going to do? Well, as it turns out, they can instead appeal to a smart contract. This is to say that what a smart contract does, in essence, is emulate a trusted third party, sort of digital Oprah, with public state. It can accomplish fair exchange, but it can also achieve essentially any functionality of which a trusted third party is capable. Okay, quick interlude. Can anyone tell me who this gentleman is? Floyd Mayweather. No, actually, it's not Floyd Mayweather, although I understand the confusion. It's Floyd Crypto Mayweather. He renamed himself over the summer, as it turns out. He, like many other celebrities, have gotten swept up in the cryptocurrency phenomenon, and he started promoting tokens sort of like Bob's Bubble tokens. What are these tokens? And what are crypto tokens? In essence, they're a sort of pseudocurrency, or application-specific cryptocurrency. They mainly take the form of ERC20 tokens, ERC20 being a standard in the Ethereum platform. And consequently, they are managed by smart contracts running in Ethereum. Their aggregate market cap is a jaw-dropping $50 billion today. They're typically sold in events known as initial coin offerings. Because there are a lot of scammers involved, the name changes periodically. But in essence, the operation is the same in all cases. They act like a sort of unregulated venture capital. You can think of them as being like shares in a company, although they don't carry the same rights, something I won't get into. The impact of tokens has been staggering. It's hard to overstate their importance. One really telling fact is that since last summer, the amount of money being poured into ICOs, into tokens, has exceeded the amount of money being invested by venture capitalists in early-stage internet startups. Now, this has been a seismic event in the venture capital community, as you can imagine. If this isn't crazy enough, there's a second type of token called an ERC721, a so-called non-fungible token that's capable of representing unique objects of potentially high value, like real estate properties, or valuable works of art, or digital cats. As it turns out, one of the most popular applications in Ethereum is something called CryptoKitties. This is an application that allows you to breed and trade cats, and some of these cats have sold for more than $100,000 apiece. Well, clearly, with CryptoKitties and ERC20s, smart contracts have demonstrated their enormous potential. But the smart contracts that manage tokens are actually technically not that interesting. They're essentially just little databases. For them to do something more interesting, more substantial, and I'll give you some examples later in the talk, we need to overcome a few critical technical challenges. And I'll talk about 3 today. The first is the problem of correctness. These contracts often have bugs, and these bugs are often very serious. I'll give you a few examples. The second problem is confidentiality. Remember, I said smart contracts have public state. Their behavior is visible to the whole world. This is great for transparency, but it's really bad for privacy. And so a tension comes into play that we somehow need to resolve. The third is a need for authenticated data. Today, it's very hard for smart contracts to get a hold of data about the real world. And this is also a fundamental problem. Let me begin by talking about the first problem, the problem of correctness. One of the side effects of the token mania is quite interesting. The smart contracts that manage tokens tend to be fairly compact. They run typically to a few hundred lines. And these contracts can hold a lot of value in the form of cryptocurrency. Consequently, the amount of money attributable per line of code to these contracts is in some case astonishing. I did a quick calculation a couple of days ago, and as you can see, in some cases, a single line of code is worth millions of dollars. This may well be the only form of software of which this is true. Well, this means, of course, that these contracts are really juicy targets for hackers. And hackers have not been remiss in taking advantage of this fact. I'll give you a few examples. The first, and probably the most infamous, of which I'm sure most of you have heard, is the so-called DAO, Distributed Autonomous Organization. It had a bug, a reentrancy bug, that resulted in the theft of $50 million. This was resolved only through a rather contentious forking process in the Ethereum platform. A year ago, a wallet, the Parity 1.5 multisig wallet, was compromised, and $30 million was stolen as a result of bad use of delegate call. It's a function for managing libraries. As a point of comparison, the largest bank robbery in the US involved only $18.9 million. And then a few months later, oh, and incidentally, this money was stolen, not entirely coincidentally, mainly from ICO wallets. And then a few months later, the same wallet was hacked again. for more or less the same reason, a bad delegate call. In this case, money wasn't stolen, instead it was frozen, and it remains frozen to this day. It's problems like these, and this is just the tip of the iceberg, that motivate the first piece of work I want to talk about today, namely our Hydra project. This is joint work with Florian Tremmer, Phil Dian, and Lorenz Breidenbach. We already have a number of ways of addressing the problem of software assurance, of creating correct or close to correct software, like formal verification. And we should absolutely use formal verification to enforce correctness in smart contracts. But unfortunately, it only scales up to programs of a fairly limited size. And perhaps more problematically, it requires that a program be shown to be correct with respect to a formal specification, which itself is a kind of program. If there's a bug in that program, you could well end up with a bug in the implemented version of the scheme you're trying to express there. To put it another way, it's turtles all the way down. Then we have things like static and dynamic verification. Should we use them? Absolutely, again. But they can only address certain types of bugs. Their scope is limited. To find a new technique, and one that we believe to be especially promising for smart contracts, we had to go back to the future. And in particular, back to the 1980s, when an idea known as N-version programming was in vogue. The goal of N-version programming was to create highly robust, one hopes correct software for embedded systems, for the type of system where you really don't want things to go wrong very often. The idea itself is simple and elegant. Instead of writing the program once, you create multiple versions in a heterogeneous way. For example, you might have different developers develop different versions of the program. They might even use different languages. And now, when an input is given to these multiple versions of the program, you take a majority vote over the output. And that is the output for the collection of program versions. This is very nice, because if something goes wrong, if there's a bug, for instance, in the first version of the program, when you take a majority vote, you'll still get a correct answer. So what's going on here? One of the contributions of our work is to reframe N-version programming in a principled and formal way. We can view N-version programming as a type of program transformation that takes as input a set of distinct expressions of a piece of code and produces as output a kind of meta-program, a framework in which these different versions are operating. Some more definitions are helpful here to understand what's going on. Let I represent an ideal program specification. This is a specification of what the developers intended when they were writing their code, of the functionality that the coders wanted to achieve. Okay, so this is something that may not have been written down, it's conceptual. Let F represent the program that was actually implemented, actually coded up. Then we define as an exploit an input such that the output with respect to I differs from that produced by the implemented program. To put this another way, the intuition here is that an input that creates a deviation from intended behavior, as expressed in the ideal program, is a bug, and it's a potentially serious one. So we'll call it an exploit. And we refer to as the exploit set, the total set of exploits that causes this type of divergence. Another important concept here, important later in the presentation as well, is a notion that we refer to as the exploit gap. Let D denote a distribution over program inputs. We define the gap as follows. What does this mean? Well, the denominator here is the weight in the distribution of all of the exploits against the transformed or combined program, against the meta program. In the numerator here, we have the set of exploits against individual heads. The total set of exploits against the constituent heads taken individually. And so you can see that if the gap is greater than 1, if the set of exploits against the individual heads has a higher weight than that against the metaprogram, then the transformation has in some sense worked. It's reduced the number of exploits. And of course, the bigger the gap, the smaller the number of exploits, relatively speaking, in the metaprogram. The better the job that the transformation is done. The gap, importantly, as you'll see, also captures dependencies among heads. So, taking a look now at n-version programming, we can see that it's a program transformation that yields a gap. Suppose, for instance, that one head, like the first head, has a bug. Well, if only one head or version of the program has a bug, the majority output will still be correct. And therefore, this bug counts in the numerator, right? It affects one of the constituent programs, but it doesn't count in the denominator. And therefore, it boosts the gap, right? Helps boost the gap above 1. But this is only true, of course, if the bug is present in one of the versions, not if it's present in all of the versions. Which is to say that in order to get a large or strong gap, we have to have independence among the heads of our program. Correlations hurt us, in other words. Right? Unfortunately, an influential paper published in the mid-'80s by Knight and Levison, in which they did an experiment. They had a bunch of undergraduates code up a piece of software in Pascal, found that the versions of a program produced by different developers, unfortunately, are not independent. We don't achieve exactly this condition we need. Worse still, NASA, it wasn't coincidence that I showed the space shuttle, NASA also experimented with n-version programming and found it just wasn't worth the money. In some cases, they were coding up 3 versions of a program, and they were only getting a 4-fold reduction in the number of errors, which just wasn't worth it from their perspective. This seems pretty damning. But we make an important observation in our work, namely that not everything is a space shuttle. What do I mean by this? I mean that not all software needs to be available at all times. And if software fails in the space shuttle, people can die. That can be fairly catastrophic. But if a smart contract fails periodically, it's really not a catastrophe. To put this another way, in many cases, it's better to have no answer than it is to have a wrong one, particularly if the wrong answer means that somebody's stealing tens of millions of dollars from a smart contract. And bugs are often harmful. This observation leads to a twist on n-version programming that we call N of n-version programming, or NNVP, or, as I'll explain a little later, the Hydra framework. Here's the idea. We're going to strengthen the majority voting that takes place in n-version programming. We'll do this very simply by taking that little module there that is implementing a majority vote, and we'll replace it with inequality test. To put this another way, we're going to do the following. Unless all versions of the program agree, we will simply abort. We'll have no output. We refer to this as a Hydra, by the way, because you can think of the different versions of a program as different heads. I've been using that term, sort of scattering my vocabulary with it. And a Hydra, of course, is a multi-headed monster. So we're creating a kind of multi-headed monster when we assemble a program in the way that I've described. Aborting in NNVP, or a Hydra program, can be viewed as a way of trading availability off in favor of correctness. And when we implement this scheme, we get much better numbers in revisiting the experiments conducted by NASA in the Eckhart et al. Paper. In particular, we get some loss in availability, but we can achieve very large gaps in the sense that I just defined precisely a little while ago. With 3 heads, according to the Eckhart et al. Experiments, or revisitation thereof, we can achieve a gap of over 4,000. With 4 heads, we can achieve a gap of almost 35,000. And in fact, we can probably achieve even better than this. Eckhart et al. Don't distinguish independent bugs in the various heads they're testing. They just view a bug as a bug. So you can see that this Hydra framework is capable of creating a strong gap. Whereas previously, a bug might have affected a program in a fatal way, now, if we just have a bug in one head, the program will merely abort. So what was previously a serious bug is now rarely going to be fatal, assuming we don't have strong correlations, or too strong, which we don't have as reflected in the fact that we're able to achieve such a large gap. Additionally, we've done a survey of the most prominent bugs in Ethereum smart contracts, things like the bug in the DAO. And in this survey, we found that smart contracts are especially Hydra-friendly, in the sense that in many cases, these vulnerable smart contracts, had they been implemented as Hydras, wouldn't have had the vulnerabilities that affected them in the wild. In some cases, the vulnerabilities are even language dependent. That means that you could, in principle, just cross-compile one version of the program into another language, create 2 or more heads, and eliminate the vulnerability. That was the case, for instance, with the DAO, which was implemented in a language called Solidity. If it had been cross-compiled to another Ethereum language like Serpent, the vulnerability, the reentrancy vulnerability that affected it could have been avoided. The main application we envisage for the Hydra framework is to bug bounties. As everyone here knows, a bug bounty is a reward given to a hacker for responsibly disclosing a software vulnerability. And today, nearly every IT firm has some kind of bug bounty program. Apple, for instance, will award hackers who disclose responsibly up to $200,000 per bug. But unfortunately, there are some problems with bug bounties as they're implemented today. 3 problems in particular. The first is that bounties often fail to incentivize disclosure. Why is this? Well, Apple, as I mentioned, is willing to pay up to $200,000 for a bug. They're willing to pay a $200,000 bounty. But if you've got a really juicy bug, like an iPhone jailbreak, you can go to another company like Zerodium and sell it for more than 7 times as much. And Zerodium will then take your bug and presumably sell it to a government intelligence agency. A second problem is that there's a time lag between reporting of a bug and action, like patching of the affected software. So the bug can often be weaponized even after the disclosure has taken place. The third problem is simply that bounty administrators often just don't pay up. Hackers often complain about this. It is often the case that they don't receive any bounty, even though they have produced a serious bug, or they don't receive a bounty as rich as expected or advertised. So suppose that we were to take a step back and try to design the perfect bug bounty. What would it look like? It would have, I would argue, 3 distinct characteristics. The first is that it would be high leverage, by which I mean that even a small bounty would incentivize a rational adversary to disclose the bug she discovers, even if the program is very valuable. The second feature it would be nice to have is automatic payout, so hackers don't need to worry about bounty administrators cheating them. It would be great if as soon as the bug is reported, somehow the money just gets paid. And ideally, it'd be nice if this feature were censorship resistant and verifiable as well. And finally, it would be nice if we had some form of automatic remediation. What I mean by that is that when the bug is reported, something instantaneously happens to the program that prevents the bug from being exploited. These are what I view as the 3 planks of the perfect bug bounty. Let me talk about how we achieve the first of them to begin with. To think about leverage, it's helpful to view bug bounties from the perspective of a financially rational adversary, an adversary that is motivated purely by money. Let's suppose that we have a program that's worth $8. Well, if an attacker identifies an exploit, he's got a choice here. He can disclose or he can attack. If he attacks, then he can earn $8, the value of the program. If there's no bounty in place, then disclosure results in no payment. So it's pretty clear what the adversary is going to do in this case. In this case, of course, the adversary will always attack. This, again, is a financially motivated adversary. So the adversary is going to choose $8 over $0. In a classic bounty scheme, where B dollars are rewarded for an exploit, it's also pretty clear how our rational adversary is going to behave. He will disclose the bug if the bounty is richer than the contract itself. In other words, if he can earn more money by claiming the bounty than by exploiting the program. Unfortunately, in some cases, programs are worth a lot of money. Right? What is iOS worth? And therefore, how big would a bounty need to be to incentivize a rational adversary to disclose? What we're after, as I said before, is high leverage. What we'd like to achieve ideally is a situation in which there's some bounty on offer, B dollars, but somehow, if the adversary attacks the program, he doesn't get $8. He gets $8 divided by some value gap, where gap, of course, we'd like to be greater than 1. And as you'll see, I don't use the term gap by happenstance here. In this case, if we're able to do this, the adversary is going to disclose if the bounty is greater than $8 divided by gap. And if the gap is large enough, this means that our rational adversary will be willing to disclose even for a small bounty. All right, but wait a minute here. You're probably doing a double take. What I'm saying here is that somehow we're going to get a rational adversary, a financially motivated adversary, not to attack, to disclose instead, even though the bounty is worth less than the contract that's being attacked. How is this possible? Well, again, I didn't use the term gap by happenstance. We're going to appeal, of course, to the Hydra framework to achieve this kind of magic. And let me explain how. What are we going to do here? We'll create a Hydra program in which, as before, if all the heads of the program agree, then everything goes smoothly. We get an output that is produced by all 3 programs simultaneously. If something goes wrong, there's a bug in one head and there's a divergence in the outputs, then, as before, we'll kick over to some fault manager and we'll abort the program. The twist here is that when this happens, we are also going to award the hacker or individual who produced the offending input with a bounty, with the B dollars. So now an adversary that's looking to attack a Hydra program faces a dilemma. She can claim the bounty now if she's found a bug in a particular head of the program. Right? She can immediately earn B dollars. Or she can decide to wait and try to attack all of the heads of the program simultaneously. Find some input that breaks all 3 heads simultaneously. But if she waits, she's at risk. She's at risk because in the meantime, some other bounty hunter may have claimed the bounty, may have claimed the B dollars. And of course, when this claim happens, the program aborts. So all of the work that the adversary invested in trying to break the 3 heads is lost. And the adversary ends up with nothing instead of the B dollars. This is the dilemma that a hacker now faces. Now, you recall that we had this notion of an exploit gap, and here was the definition, but you don't need the definition to understand what I'm going to explain now. We can see that the Hydra framework gives us high leverage in exactly the sense that I've been describing. Suppose, for instance, that we have an extremely strong adversary, a rational adversary, one that is able to discover bugs as fast as the rest of the community of honest bounty hunters combined. This is a fairly strong adversary. let's suppose that our contract is worth A dollars, and let's suppose that the bounty, again, is worth B dollars. What we're able to prove in our paper is that this rational adversary will be incentivized to disclose, provided we meet the condition that the bounty is greater than A dollars, the value of the program, divided by the gap, plus 1, little extra term. But essentially, we've achieved exactly what we were looking for. What does this mean in practice? Well, let me give you an example. Recall that those NASA experiments, when we revisited them, implied a gap of over 4,000 if we have 3 heads, and of about 35,000 if we have 4 heads. What does this mean? Well, suppose that we take as an example an extremely valuable contract for one of the most valuable tokens, like Omise Go, which as of yesterday was worth something like $1.7 billion. And let's suppose that we implement the smart contract with 4 heads. So we have a gap of almost $35,000. It turns out then that a bounty of a mere 50K is sufficient to incentivize the adversary to disclose. And 50K is a fairly modest bounty. This is well within the range of typical bounties in most bug bounty programs. So we've achieved high leverage. How about automatic payout? Well, remember that all this is occurring in a smart contract. And smart contracts are designed exactly to do automatic payouts on trigger conditions. This is what smart contracts do. So we get automatic payout automatically, just by merit of the fact that we've implemented this thing as a smart contract. Okay, that was fairly easy. How about the third property, automatic remediation? This raises an important question. What do we do if a contract fails? How do we remediate? What action should we take? Well, for a good answer, we can look to the history of smart contract failures in Ethereum. In the case of the DAO, as I mentioned, there was a contentious fork. What this fork did was return money to the victims affected by the exploit of the smart contract. How about the parity multisig hack, that contract that had $30 million stolen from it? What happened? Well, the $30 million were essentially lost forever, but a bunch of white hat hackers stepped in and stole, in quotes, the money that had not yet been taken by the hacker, and they returned this money to the victims. And incidentally, 2 of the co-authors of the Hydra paper were part of this team of white hat hackers. How about the second parity multisig hack, the one in which money wasn't stolen, but a whole lot of money was frozen? Well, nothing has happened yet, but the proposed remedy is to unfreeze the funds and return them to the victims. So you see a theme here. In many cases, at least if a smart contract is financial, it makes sense when something goes wrong simply to return the money. In other words, we can have the fault manager in our program now not just abort, but as soon as the bug is detected, return all the money to the users represented within the smart contract. So we now achieve all 3 properties we were after in the perfect bug bounty. Just to summarize, smart contracts we see as perfect targets for the perfect bug bounty. To begin with, they're highly vulnerable. This is something we've seen already. They're very bug prone. They're hard to code correctly. And they're in many cases highly valuable. And again, the number of dollars attributable per line of code can reach into the millions. But they're very promising. They're Hydra-friendly in the sense that I mentioned earlier. When we did a survey of contracts in Ethereum, vulnerable contracts, we found that if implemented as Hydras, the exploits we've seen in the wild wouldn't have been a problem. Second, they support the 3 properties that we were after in our ideal bug bounty program. And we get a bonus feature here, something I haven't talked about yet. namely that we can automatically tell how much a program is worth. This is true of smart contracts. It's probably true of essentially no other type of software. And therefore, we have the first opportunity to reason about bug bounties and bounty amounts in a principled way. How do we tell how much a smart contract is worth? Well, we just look it up in the marketplace. I can tell you within a minute how much Omise Go is worth, for instance. I just consult one of any of numerous websites to determine the current market value. This, as I said, is an unusual and very attractive feature because it means, among other things, that we can adjust bounty amounts dynamically. We can actually change them on the fly. You can't do this for any other type of software. We've implemented as a Hydra contract a standard ERC20 token, one of the token contracts that I talked about earlier, and we've staked our own ether in the contract so that you, if you're able to exploit the contract, can go and claim a bounty. This is a relatively small amount, but it's sufficient to protect a program that's worth millions of dollars, as you'll appreciate, given the gaps that I cited earlier. And this is deployed on the Ethereum mainnet, so you can go attack this thing today. I'll give you a more convenient pointer a little later. We're in the process of implementing a second Hydra contract in the form of a generalized Monty Hall type game. This should be coming out soon. Okay, to take a step back, I've talked about the problem of correctness. Now I'd like to talk about the two other smart contract challenges I enumerated, namely confidentiality and authenticated data. And in particular, I'd like to talk about a project called Town Crier. This is a project we've been working on for a couple of years. It first went live in the Ethereum mainnet about 6 months ago. Here's a popular example of a smart contract that people regard as very promising and interesting. You can implement a flight insurance scheme as a smart contract in such a way that payouts are automatic. In particular, when you're about to fly, you can send to the smart contract a specification of the policy size you would like, along with payment of the associated premium. So if you're buying, say, a $100 policy, you might have to pay $1 for the policy, and the details of your flight. If your flight is delayed or canceled then, the smart contract can pay you automatically. It just spits out $100. This is very nice because it means that you don't need to deal with the insurance company. You don't need to fill out forms. And insurance companies, of course, are notorious for not wanting to pay out. In this case, the payout happens automatically and instantaneously. So this, as I said, is a very popular example illustrating the capabilities, the promise of smart contracts. But somehow, the smart contract here needs to know whether or not your flight was delayed. And in general, if you think about all the applications to which you could put smart contracts, you'll see that really interesting examples are naturally data hungry. If we're talking about a financial smart contract, well, it's likely to need access to equity prices or commodity prices. If we're talking about an insurance policy for farmers, it's going to need access to data about weather. If we're talking about a betting smart contract, well, it may need access to results in sports. So you can see, again, that interesting smart contracts need to know what's going on in the real world. There's a problem here, though, which is that smart contracts, for various technical reasons having to do with the underlying consensus algorithm in the blockchain, don't have internet connections. There is no good way, even if there is a website that can be trusted to serve correct data, there's no good way for a smart contract to reach out and get the data from the target website. What we've built in Town Crier is what's often referred to as an oracle. This is a service that acts as a bridge between websites and a blockchain, or between websites and smart contracts. In particular, if a smart contract needs to know a particular piece of information, if it's got a question in mind, chances are that somewhere out there, there's a website or a collection of websites that everyone trusts to return a correct answer. In this case, town crier will relay the answer from the website to the smart contract. It'll actually push this data onto the blockchain. But now you're thinking, okay, this is all nice, this is well and good, but why should I trust a bunch of academics to implement this thing correctly? Right? Academics are notoriously bad at operational security, among other things, right? So why should I trust you to secure the server that's running town crier correctly? The answer is you don't need to trust us. And the reason is that we appeal to a technology, which you'll hear about in some other talks at this conference, known as a trusted execution environment, and to Intel SGX, software guard extensions, a new instruction set architecture extension available on recent model Intel CPUs. SGX allows a program to run in a protected environment known as an enclave. And an enclave confers a couple of important security programs on the properties on the program it's executing. The first is integrity. It's infeasible, assuming you trust SGX, it's infeasible for the operating system and other processes and even the owner of the physical host to tamper with the control flow of the program. That's the first property. The second key property here is confidentiality. Again, the operating system, other processes on the host, and even the owner of the host cannot learn anything about the state of the program. There's some important caveats here I won't get into, but this is essentially the property that SGX is driving at. So it achieves a kind of black box execution of a program in which this box cannot be tampered with in the sense of integrity or confidentiality by any other program or the host owner. Another thing that SGX does is provide a facility known as remote attestation. In particular, the program can produce a kind of certificate that proves to a remote party that a particular program is running in the enclave. And it does this in a way such that you can bind a public key to the program, where the program itself holds the corresponding private key. This is very nice because it means that now that this remote user knows that anything that's been digitally signed with SK sub X was produced by a program whose identity she knows. And it also, of course, enables this remote party to communicate securely with the enclave. It's possible to create a secure channel or encrypt data under the public key such that only the enclave can decrypt. So, as I said, the beauty of town crier here now is that you don't need to trust us. You only need to trust the hardware to achieve the properties we're after. This sounds great, but let's take a look at our example here again. There's a looming problem, a serious problem here. Our hapless user, you'll recall, sent to the smart contract a specification of the flight she was on. She gave her flight itinerary to the smart contract. And remember that smart contracts, again, have public state. Everything they do is visible on the blockchain. So this poor user now has revealed her travel plans to the whole world. This is obviously a serious privacy problem. And this is a problem that vexes many smart contracts. This is part of the fundamental challenge of confidentiality that I articulated earlier. What do we do about this? Well, to solve this problem, we can appeal to the second property of the enclave that I mentioned before, namely confidentiality. And in particular, rather than sending her flight itinerary directly to the smart contract, the user can instead send it into the enclave. She can establish a secure channel with the enclave and send her flight itinerary to the enclave. The program running in the enclave then can check whether her flight was delayed or canceled without revealing her flight details to the smart contract or on the blockchain. I mentioned town crier in part because it helps address the problems of confidentiality and authenticated data that I've mentioned as serious challenges in realizing the promise of smart contracts. But I also mention it because it points to an very important technical and research idea. It illustrates what I would consider to be an important research problem. This stems from the observation that in some sense, blockchains and SGX are trying to achieve the same thing. They're very different technologies, but they have a very similar goal. In some sense, they're both trying to instantiate this digital Oprah I talked about near the beginning of the talk. In both cases, they're trying to emulate a trusted third party. But they do this in strongly complementary ways. Blockchains offer high availability and persistence of data. This is their basic value proposition, in fact. But they don't offer any confidentiality, as I've explained, and it turns out that their performance is actually quite poor because they're distributed systems and a given workload is executed many times by a collection of players who need to reach consensus. In contrast, SGX doesn't offer availability and it doesn't offer persistence. If the machine is power cycled, you're out of luck. But it does offer confidentiality, as explained before, and it turns out it offers fairly high performance. The performance overhead imposed by enclaves is relatively modest. So, as I said, we have two complementary approaches to the same problem. If we can unify these two approaches, we can perhaps achieve the best of both worlds. But unifying them in a secure and principled way turns out to be somewhat challenging. This is a challenge that we've taken up in a very recent project called Ekiden, a project whose paper is currently under submission. It involved a team at Berkeley, Cornell, Cornell Tech, and UIUC. The idea behind Ekiden is simply to execute smart contracts in enclaves rather than executing them on a blockchain. Why would we want to do this? Well, there's several benefits. The first is low cost. We only need to execute a smart contract once if we're executing it in an environment we trust, like an enclave. A second benefit is scalability. Remember, I said that enclaves deliver fairly good performance. We can take advantage of this in the blockchain as a whole if all smart contracts are being executed in this manner. And the final benefit, of course, is confidentiality, as discussed. A smart contract and the data it's operating on, like the flight data of the user in the example I gave, can be concealed in the enclave and protected against prying by the operating system and other applications. We've implemented a number of example applications, including machine learning models and smart contracts, privacy-preserving tokens, various games, and also, quite importantly, a secret CryptoKitties breeding algorithm. As it turns out, the breeding algorithm for CryptoKitties was meant to be secret when the contract was deployed, but the algorithm was sitting on the blockchain and quickly got reverse engineered, and of course, taken advantage of by people who wanted to breed very valuable CryptoKitties. If we use Ekiden, we can instantiate this algorithm in a black box way, making it much harder to reverse engineer the breeding algorithm. These are just a few examples of what you can do with this type of platform. Okay, the paper will be released in a few weeks. It's not available quite yet. To wrap up here, if you're interested in learning more about Hydra contracts, I'd encourage you to visit our Hydra project page at thehydra.io. You'll find code that will allow you to experiment with the framework. You'll find our ERC20 bounty. You'll find the paper, and so on and so forth. So please visit the project website. If you're interested in learning more about Town Crier, similarly, we have a project website. And as I mentioned, Town Crier has been running, or is a public service on the Ethereum mainnet. It's been running for about half a year now. It's free. It has only a limited number of data feeds, but you're welcome to go play with it, and we would encourage people to contact us if you're interested in extending the service. I'll mention that this was actually, according to Intel, the first recorded public-facing production service to make use of SGX. And finally, let me mention that all this work has taken place under the aegis of the Initiative for Cryptocurrencies and Contracts, or IC3, of which I'm a co-director. The initiative includes 16 faculty across 8 campuses, and there are lots and lots of interesting projects going on, like alternatives to Town Crier, the TLSN system, like other types of privacy-preserving smart contract systems, the Hawk system, and so on and so forth. We're doing quite a bit of work that I would consider to be interesting and useful, so please visit our website. Thank you.
Robert Broberg, Cisco Systems. Very cool work. Could you comment a bit more on the fault manager? Because you've gone from majority voting now to, I didn't quite understand what the fault manager would do. I mean, how is it going to go fix one of the heads, or what actually occurs at that point when it sees something wrong?
Yeah, so what the fault manager does is quite simple. It just aborts when it detects that the outputs of the various heads diverge. That's all it does. Right. So you may also remediate in the case of a bug bounty. In that case, you return the money in the smart contract to the users. And the logic can be fairly compact for this. Right? So it's not a big piece of code.
Hi there, Matthias Peyer, Purdue University. Inspiring talk, thank you. Quick question regarding the town crier that you presented. I haven't read the paper, but I wondered, didn't you just include the web service Flight Radar 24 in your attack surface? Now, if I get hold of that service that then gets fed into town crier, I can control the smart contract by extension, right?
Yeah, very good question. What happens if the data at the source is corrupted? All town crier does is act as a bridge between the website and the smart contract. There's no way for it to check whether the response is correct. What you can do, though, is source data from multiple websites and take a majority vote. Got a running theme here. But if you don't have access to secure data or trustworthy data anywhere, you're in trouble to begin with, right? There's basically no way for a smart contract to learn about real-world state if all data has been poisoned.
This is Xiaofeng from Indiana. Very interesting work. And I'm particularly intrigued by your work running this verification inside the enclave. But my question is, you're talking about this is not easy, but could you, explain to us what is the technical challenge? I know implementation is non-trivial, but is there any technical challenge you need to overcome? And also another related, one thing I can imagine is enclave well-known has this side channel problem. And it's exactly can be used by adversary to figure out the confidential information. But just do you think this is a kind of challenge you want to address? Thank you.
Right, so what are the technical challenges? Obviously, I didn't get into details here. This is discussed in the paper. The main technical challenge, as I see it, is keeping the TCB small for the code that's running in the enclave. And enclaves don't provide network stacks. So you actually need to rely on the operating system to do the networking for you. You don't want to bloat the TCB, as I said, by running a blockchain client in the enclave. So the question is, how does the code in the enclave know that it's getting a correct query from the blockchain if it's operating in the presence of a hostile network adversary, namely the platform itself, and it's not running a client? This is one of the technical challenges we need to overcome in Town Crier, and there's some others discussed in the paper. As for side channels, yes, I didn't have a chance to get into them. I'm happy to talk offline about that issue.
Hi, Michał Kruk from UCL. Really nice talk. I wanted also to ask a question about this Town Crier. I recently seen there is Oraclize. I don't know if you know the project. So basically the goal is the same. However, they run the service as a smart contract, and then they give you a response from a remote HTTPS server, and they provide you with a proof using TLS notary. Could you refer what are benefits of your solution over this, or how would you compare such?
Yeah, so Oraclize is a popular Oracle service. It, as you said, uses a combination of its own service and TLS notary to try to ensure the correctness of the responses that are being provided. TLS notary, from what I've seen, has not been maintained for some years now. And more fundamentally, the problem here is that you've got two services run by relatively small entities. Oracleize it is a, I don't know, 2 or 3 man shop. TLS Notary, as I said, doesn't seem to have been maintained for a while. You've got two services. If both services are corrupted, you're in trouble. So you are relying on the reputation and the OPSEC skills and so on and so forth of two small teams without a very strong assurance that they're doing things right. That's one issue. This is part of the reason that we regarded this as a basic problem and why we started doing research in this area. The other issue, of course, with a service like Oracleize is that there's no way for them to provide confidentiality. So it's been a very important service in as much as it was one of the earliest Oracle services in the Ethereum ecosystem, and it's been a very helpful catalyst. But its security is limited. This is something one needs to recognize.
However, if you have because it's deployed as a smart contract, so you can easily verify. I get the argument about the small team, but if it's a smart contract, you kind of know what it actually does.
You might be able to verify retroactively. I don't know exactly how their smart contract works.
Okay.
I don't know the details. The system has evolved, so I don't know exactly what they're doing today.
You mentioned earlier that you use blockchain as well as SGX, but in your later paper that you actually remove a lot of the functionality from the blockchain and move it to SGX. So what is the role of the blockchain in the later portion?
So the blockchain can play an important role even when you're using SGX in a couple of different senses. One, there's a question of how you order transactions performed by various enclaves in an authoritative way, how you serialize them. You need some authority to do this, and that's essentially what the blockchain is doing. The other thing that the blockchain can buy you is the property of persistence, as I said, which SGX doesn't give you. So in particular, you can checkpoint enclave state on chain. That way, if a node goes down, you can recover your state. So they really do have complementary properties that it's helpful to leverage simultaneously to achieve, as I said, basically the best of both worlds, with some provisos.
Hi, Ari. I'm Trent Jaeger at Penn State. Nice talk. Thanks. I had a question about the incentivization that you discussed with respect to Hydra. And so when you evaluated the model, you compared an adversary to all honest defenders who are trying to find a particular bug. And you had this sort of equality between them, where if the adversary was able to work as well as all the honest parties, then that would be a very strong adversary. Challenge is that that's kind of the state we're in now, where we have, one adversary finds a bug, and supposedly all honest adversaries are fuzz testing and doing things to find these flaws, and we're still losing. But what I was curious about also was there was this notion in Hydra that you had to find multiple bugs in the different versions, and I didn't see that in the model exactly. How did that play in?
Yeah, good question. So why is it that an adversary, in order to exploit a Hydra contract, has to find bugs in multiple heads? And the reason is because they need to find some input that produces an erroneous output, but at the same time doesn't cause a divergence in the outputs of the various heads. So they need to find some input that's going to cause every head to fail at the same time in exactly the same way. And achieving that type of convergence, of course, is hard. This is why we're able to achieve a high gap in the way that we are.
Does that depend on the type of bugs? I mean, if you make a logical bug and it spans all of them, spans all of the heads, then I guess that would be, you just need one input there.
Yeah, so if you've got a collection of bugs that affect all heads, that's another way to state that is that you've got strong correlation among the set of bugs in the various heads. And as I said, correlation hurts. Our measurement of the exploit gap, this empirical measurement, is meant to capture the degree of independence among heads, among other things.
Okay, thanks.
Hi, Allison Mankid, Salesforce and IRTF. Really great talk. I'm looking forward to reading the Ekiden paper, too. And I wanted to ask, you said we don't need NASA-style availability, but it seems like it would be worthwhile to do some formal assessment of the availability issues here if you're thinking about putting this into business contexts where 5 nines might not always be needed, but 3 nines certainly is. Is that a wing of the research that you're looking into?
It's certainly desirable that a smart contract not go down. The point I was making is that it's much better that a smart contract abort than that the money be stolen. And so this is an instance of a system where, in many cases, aborting is better than emitting an erroneous output. If smart contracts are used to power IoT devices, critical systems, then availability does become much more important. This is not something we've thought deeply about yet because smart contracts aren't there yet.
Sure, but they're going to get a broader range of uses, and this kind of work makes it even more compelling. So
where availability is critical, you would have to go back to end-version programming. And if you're careful, maybe you're able to achieve a reasonable gap, not as strong as you would achieve with the Hydra framework, but still possibly beneficial enough to justify the cost. NASA, again, found the cost was not justified, but it's possible that their development regime or whatever was just not sympathetic to the goal.
Thanks.
Atul Prakash, University of Michigan. Great talk, really enjoyed it. So just on the last response you made, I'm wondering whether you can play like a strategy of like trying to undermine a smart contract by, let's say one of the heads has a fault you know about, and let's say the crash actually happened, and this sort of gives a timing, and if you can take advantage of the timing to not pay the contract by inducing that failure, so that the money is returned to all the parties, the contract is void at that point, and so you don't actually have to pay. And there might be some perverse incentive in basically leaving some bugs or knowing about some bugs and using them to void contracts to avoid, say, an adverse payment. Is that possible, and is that something you're worried about?
Yeah, in general, we haven't taken these sort of exogenous considerations into account in the development of our model. One certainly could expand the model to consider the cost of denial of service attacks against a contract by a hacker that has discovered a bug in one head. That's just out of scope for the paper as we developed it.
Okay, great.
So as somebody who doesn't know all that much, or didn't know before your talk all that much about blockchain, now I feel like you've solved a huge number of problems. So in your opinion, where does this leave us with blockchain and smart contracts? Right? Is there still a tremendous amount to do? What are the main challenges remaining?
That's an excellent question. How much more is there to do? As I mentioned, most smart contracts today are not all that technically interesting. Now, the vast majority of the value locked up in smart contracts is in ERC20 tokens. Now, we have a long way to go before smart contracts are interfacing with IoT devices, are helping manage supply chains, are helping people negotiate real estate transactions, and so on and so forth. These are things that the community has envisioned, but they haven't become a reality yet for a number of reasons. Some of them are security related, relate to the challenges that I articulated. Many of them are business related. So blockchain technologies and smart contracts in particular are really in their infancy. The ability of blockchains to solve problems is also, not surprisingly, greatly overstated. This is a much hyped technology. It's sort of like crypto, right? It's regarded as a magic pixie dust. There was an iced tea company, Long Island Iced Tea, that renamed itself Long Island Blockchain, and saw its stock price surge by a factor of 10 or something. Right? It doesn't have magical properties on that order. There are problems and interesting problems it can solve, but there are a whole lot of problems it can't solve. And I think the community is still trying to distinguish between these two classes of problem. So we have a long way to go. Thank you.
on break until 11 o'clock.